welcome to another explainer. We love taking these complex ideas and mapping them out visually so we can all truly see the big picture. Today, we're embarking on a pretty fascinating 140-year journey of screen technology. We're going to trace the entire evolution of the television, literally from crude, noisy mechanical parts invented way back in the 19th century, all the way to the microscopic, non-organic light emitters that are poised to totally dominate our living rooms in the future.
But first, I want to start by asking you a question. What does a noisy, spinning piece of cardboard from 1884 have to do with a sleek, high-definition screen you're looking at right now? It sounds like a completely bizarre combination, doesn't it? But there is actually a direct, linear connection between those 19th century mechanical discs and the absolute bleeding edge of modern display tech. You see, the core problem, how to slice an image up, transmit it, and beam it straight into your eyes, well, that's been the exact same for over a century. The only thing that's really changed is how we solve it.
Section 1. Dawn of Mechanical TV, the NIPCO disc.
Okay, to really understand this journey, we have to step into the time machine and go right back to Berlin in 1884. And this beautifully illustrates the foundation of the whole shebang, the NIPCO disc. Patented by Paul Gottlieb Nipkow, this wasn't some sleek digital screen. No, it was a mechanical, rotating image scanning device. Just imagine a spinning disc made of metal or cardboard with a single turn spiral of little holes drilled right into it. As that disc rotated super fast, a lens would project an image onto it, and each hole in the spiral would take a tiny visual slice through the image. It basically broke a picture down into scan lines, line by agonizing line.
Now, looking back at this tech graveyard today, early TV viewing was, honestly, completely absurd by our modern standards. Because you were totally reliant on physical holes in a spinning disc, the maximum number of scan lines ranged from just 30 to maybe 100. So what does that mean? It means the resulting image was about the size of a postage stamp. And to enjoy this tiny, terrible, flickering picture, early TV watchers had to sit there and endure a heavy, incredibly noisy machine just clattering away in their room. Plus, actually capturing the video required blindingly powerful lighting just to register through those tiny holes. So yeah, clearly clunky mechanical parts were not going to be the long-term answer.
Section 2. The Plasma Display Revolution. Ditching the moving parts.
We absolutely had to ditch the moving parts. And the ultimate solution to those mechanical TVs was a total shift into the realm of advanced physics and gas discharge. Okay, let's dive into this because the physics here are just incredible. It all starts when electronics shoot a voltage pulse into a microscopic cell. This trapped mixture of neon and xenon gas gets ionized, turning instantly into a plasma. That plasma state causes high-energy collisions emitting invisible UV photons, which then strike the cell wall's phosphor coating, and bam, it bursts into visible red, green, or blue light. And if it needs to dim the brightness, it just rapidly flickers that cell on and off hundreds of times per second.
So the absolutely crucial point here is this self-emissive magic. Unlike early LCDs that required this big glowing backlight panel behind the screen, every single pixel in a plasma TV was its own independent light source. Think about that. If a pixel needed to be black, it literally just turned itself off completely. This gave plasma perfect blacks, infinite contrast, and near zero motion blur. It's exactly why plasma became the undisputed gold standard for watching sports and building high-end home theaters. But despite having arguably the most beautiful picture on the market at the time, plasma suffered a pretty tragic and rapid demise.
Section 3. Why plasma went extinct. The autopsy. By 2014, mass production had completely ceased. If you're wondering what killed such a perfect picture, well, just look at the sheer physical reality in these numbers. Compare a 60-inch plasma from its peak era to a standard LCD of the same size. A plasma weighed somewhere between 60 to 80 kilograms. Guys, that is up to 175 pounds. The LCD, less than half that weight. And then look at the power draw. An LCD pulled around 100 to 200 watts, while the plasma was just sucking down 400 to 600 watts of electricity. Let's be honest, absolutely no one wants a 175-pound TV that acts like a 600-watt space heater in their living room. And beyond the crazy weight and the heat, there were a few final fatal flaws. That massive power consumption actually started violating global energy efficiency regulations. Then you had the dreaded burn-in risk. Static images, like news tickers or video game HUDs, could permanently scar those beautiful phosphors. The heavy gloss fronts were highly reflective, which basically ruined daytime viewing.
And finally, just manufacturing these massive glass panels with vacuum-sealed rare gases was incredibly expensive. So by 2014, heavy hitters like Panasonic and Samsung just threw in the towel and completely abandoned plasma for cheaper, lighter LCDs.
Section 4. The modern OLED landscape. The self-emissive comeback.
But the desire for perfect blacks and infinite contrast definitely didn't die with plasma. Enter OLED, which stands for Organic Light Emitting Diode, a tech that managed to resurrect that self-emissive pixel, but without all the baggage. Notice the physical footprint here. OLED gives you like 95% of plasma's subjective strengths, including those gorgeous, inky, perfect blacks because each pixel can turn itself off. But it does it all in an ultra-thin package. We're talking a totally manageable 20 to 25 kilograms, and they are vastly more energy efficient. It pretty much entirely solved the weight, power, and thickness problems that put plasma in the grave.
Section 5. Micro-LED, the final frontier.
Now, OLED is amazing, but it isn't perfect. It relies on organic compounds, which means eventually it can degrade or suffer from burn-in over time. And that brings us to the absolute bleeding edge of our screen evolution. We are talking about a technology that market analysts forecast will totally dominate a $300 billion display market by 2035. Now, what's really interesting about this microscopic RGB structure here is the material breakthrough. Unlike OLED, micro-LED uses non-organic microscopic emitters to create light. And because it doesn't rely on organic compounds to glow, it suffers from absolutely zero degradation. It's basically the holy grail of pixel construction.
In fact, industry experts and display scientists are referring to micro-LED as having the ultimate no-compromise screen quality. It's super important to grasp that this isn't just some minor refinement, like adding a slightly better backlight to an LCD. No way. This is a true once-in-a-generation display revolution, totally on par with a massive jump from those old tube TVs to the first flat panels.
Micro-LED really represents the perfect blend of literally everything we've learned over the last 140 years. It gives you the perfect pixel-level absolute black and infinite contrast of an OLED or classic plasma. But because it's non-organic, it magically solves the remaining flaws. It provides extreme, blinding peak brightness for daytime viewing, unprecedented physical durability, and absolutely zero risk of screen burn-in. It is, by all physics and metrics, the flawless display.
So let's take a step back. We started with a spinning, perforated piece of cardboard all the way back in 1884, right? And today, we've arrived at microscopic, non-organic pixels that deliver just reality-bending perfection. This 140-year hardware journey is finally reaching its peak. The perfect screen is almost here. But that leaves us with one final, pretty provocative question to think about. Once the hardware is utterly flawless, what incredible content are we actually going to be watching on it? Thank you so much for joining me on this explainer. I really hope this helped you see the big picture.